You open the app and the feed already knows. The next video, the next song, the product you didn't know you wanted, served in under 200 milliseconds, chosen from a catalog of 100 million things. So in the interview, they ask you to build it, and here's the trap almost everyone walks into. They reach for the model. I'll train a neural network to score how much this user will like each item. Great. Now score 100 million items for every one of 100 million users in 200 milliseconds. That is mathematically impossible. It's not a tuning problem, it's a wall. A complex model scoring 100 million items for one request would take minutes, and you have milliseconds. So the entire secret of a real recommender is this. It is not a model. It's a funnel. You never score everything. You use something cheap to throw away 99.9% of the catalog in a few milliseconds, and then you spend your expensive model only on the few hundred survivors. Get that one idea. Retrieval, then ranking, cheap, then expensive. And every large-scale recommender on Earth suddenly makes sense. Miss it, and you fail the interview in the first 2 minutes. Let's frame it before we build. Functional. Given a user and a context, return a ranked list of items they're likely to engage with. Videos, posts, products, songs. Personalized, fresh, and diverse enough that it's not the same 10 things forever. Clarifying questions that signal seniority. What are we optimizing? Clicks, watch time, purchases, long-term retention. Because the objective changes the whole design, and engagement and satisfaction are not the same thing. What's the catalog size, and how fast does it change? A movie catalog is stable. A social feed turns over every minute. And what signals do we have? Explicit ratings, or far more common, implicit feedback. Clicks, watches, skips, dwell time. Non-functional is where it bites. This is on the hot path of every app open, so serving latency is a hard budget, around 200 milliseconds, end to end. It must scale to hundreds of millions of users and items, stay fresh as new items appear. And, say this out loud, it's a machine learning system. So it has two totally different life cycles bolted together. Offline training and online serving. Naming that split early is a senior tell. Do the math, because the numbers are what force the architecture. Say 100 million items in the catalog, 100 million daily users, each requesting a feed maybe 10 times a day. That's 1 billion recommendation requests a day. Low tens of thousands per second. Call it 100,000 at peak. Now the killer constraint. Suppose your ranking model takes just 1 millisecond to score a single user item pair. Already optimistic for a deep model. Score 100 million items for one request, and that's 100,000 milliseconds, over 1.5 minutes for one feed load, against a 200 millisecond budget. You're off by a factor of 500. No hardware saves you. You cannot buy your way out of 2 orders of magnitude per request, times 100,000 requests a second. That single calculation is the entire justification for the funnel. You must cut the candidate set from 100 million to a few hundred before the expensive model ever runs. So the design isn't which model, it's how do I avoid scoring almost everything. That reframing is the whole interview. Here's the shape every modern recommender takes. 3 stages, cheap to expensive. Stage 1, retrieval, also called candidate generation. Its only job, from 100 million items, get to maybe a few hundred plausible ones, fast, in a few milliseconds. It's allowed to be rough. High recall, low precision. It just has to not miss the good stuff. Stage 2, ranking. Now, and only now, the heavy model runs. But on a few hundred candidates, not 100 million. It scores each precisely with a rich model and lots of features, and sorts them. This is where the accuracy lives. Stage 3. Re-ranking. Take the ranked list and adjust it for things a pure relevance score ignores. Diversity, so it's not 10 near-identical videos. Freshness, business rules, filtering things they've already seen. The mental model to say out loud: retrieval maximizes recall cheaply. Ranking maximizes precision expensively. Re-ranking enforces the constraints. Each stage narrows the set and raises the cost per item. 100 million to hundreds, to a final 10 or 20. Draw that funnel and you've already given a staff-level answer. This is the cleverest part, so we go slow. How do you find a few hundred good items out of 100 million in milliseconds without a model touching most of them? The modern answer is embeddings, plus approximate nearest neighbor search. First, embeddings. You represent every user and every item as a vector, a list of, say, a few hundred numbers. Learned, so that similar things sit close together in that vector space. A user's vector lands near the items they'll probably like. Now recommendation becomes a geometry problem. Find the item vectors closest to this user's vector. The model that learns these is the two-tower model. One neural network tower encodes the user. A separate tower encodes the item, and they're trained, so a user and an item they engaged with produce vectors with a high dot product. The beautiful trick: because the towers are separate, you can compute every item's vector offline, in advance, and store them. At serving time, you only compute the user vector, one small forward pass, and then search. But searching 100 million vectors exactly is still too slow, so you use approximate nearest neighbor, ANN, with an index like HNSW. It trades a tiny bit of accuracy to find the closest vectors in logarithmic time instead of linear. Pre-compute item vectors, embed the user live, ANN search the index, get your few hundred candidates in single-digit milliseconds. That is how you search 100 million items without scoring 100 million items. One more layer, because real systems don't use a single retriever. And saying this is a strong signal. In production, you run multiple retrieval sources in parallel and blend them. The two-tower embedding retriever is one source. But you'll also pull candidates from recent popular items, so nothing viral is missed, items from creators or categories the user already follows, collaborative signals users like you also watched, and freshly uploaded items that have no engagement history yet but need a chance. Each source is cheap and high recall in its own way, and you union their outputs into the candidate pool that goes to ranking. Why multiple sources? Because any single retriever has blind spots. Pure embedding similarity over-recommends what's already similar to your history and starves discovery. Popularity alone ignores personalization. Blending sources is how you get both relevance and coverage. The senior framing. Retrieval is a recall problem solved by an ensemble of cheap sources, and the ranking model sorts out the precision afterward. Naming even 2 or 3 distinct sources, embeddings, popularity follows, shows you've seen a real system, not just a textbook. Now the survivors, a few hundred candidates, hit the ranking model, and here the constraints flip. You have few items and can afford to be expensive and precise. The ranker is a heavy model, historically gradient-boosted trees, today usually a deep neural network, that takes a user item pair plus a pile of features and predicts the probability of the outcome you actually care about. Click, a long watch, a purchase. Features are the whole game here, And they come in types: user features, history, demographics, long-term interests, item features, category, age, popularity, the item embedding, context features, time of day, device, what they just watched, and, the highest signal ones, user item cross features. Has this user watched this creator before? How many times? Those features come from a feature store, a system that serves them at low latency online and, critically, computes them the same way offline for training, so you don't get train-serve skew. Modern rankers are often multitask, predicting click and watch time, and like simultaneously, because optimizing a single metric like click-through breeds clickbait. You then combine those predicted probabilities into one score. The output, your few hundred candidates, now precisely ordered. Ranking gives you the most relevant list, but the most relevant list is often a bad list, and knowing why is a staff-level insight. Rank purely by predicted engagement, and you get 10 nearly identical videos, a filter bubble, clickbait at the top, and nothing the user hasn't seen. So the final re-ranking stage deliberately perturbs the perfect relevance order to serve goals relevance ignores. Diversity. Techniques like maximal marginal relevance, MMR, penalize an item for being too similar to ones already in the list, so the feed has variety. Freshness and exploration. Inject some newer or uncertain items so the system keeps learning and doesn't ossify. Business rules, sponsored slots, don't recommend what they just bought, content policy filters, and the deep trap to name, the feedback loop. A recommender trains on the data it generates. It only sees engagement on what it chose to show. Optimize engagement naively, and it narrows into a self-reinforcing bubble, and your offline metrics look great while the actual experience rots. Fighting that, with exploration, diversity, and long-term objectives, is one of the hardest real problems in the field, and naming it unprompted is exactly what separates senior from staff. Step back and see the two life cycles, because an ML system is really two systems. Offline is the training world. You collect logged interactions, every impression, click, watch, skip, through an event pipeline like Kafka into a data lake. You generate training labels from them. You train the two-tower retrieval model and the ranking model on huge batches. And you pre-compute all 100 million item embeddings and load them into the ANN index. This runs on a schedule. Many teams retrain daily or even hourly. Online is the serving world, living inside that 200 millisecond budget. Embed the user, ANN retrieve candidates, fetch features from the feature store, run the ranker, re-rank, return. The two worlds must agree on one thing, or everything silently breaks: feature consistency. If a feature is computed one way in training and another way in serving, that's train-serve skew, and it quietly destroys model quality with no error message. The feature store exists precisely to guarantee they match. Saying offline trains and pre-computes, online serves within the latency budget, and the feature store keeps them consistent is the sentence that shows you understand ML systems, not just ML. The follow-ups that show range. Cold start, a brand new user or item has no history, so embeddings are useless. New users fall back to popularity and demographics, then personalize as signal arrives. New items use content features, the item's text, category, creator, to place it in embedding space, and use exploration to give it impressions. Offline versus online metrics. Offline, you measure recall at K and NDCG, but they only correlate with the truth. The real verdict is an online A/B test on live engagement, and the offline-online gap is why you never ship on offline numbers alone. Freshness and real-time for fast-moving feeds, update user vectors, and features from very recent activity, not just yesterday's batch. Position bias. Users click the top item because it's on top, not because it's best. Your training labels are biased by the very positions you chose, and you have to correct for it. And the scale of the ANN index, 100 million vectors, is tens of gigabytes. It's sharded and replicated and rebuilt as embeddings change. Each of these is a crisp one-liner that shows range. The red flags, the traps that sink candidates. 1. Trying to score the whole catalog with one model. That's the latency wall. Use the funnel. 2. No retrieval stage at all, ranking everything, physically impossible at scale. 3. Never mentioning embeddings or approximate nearest neighbor for retrieval. That's the modern core. 4. Optimizing a single metric like click-through. It breeds clickbait. Go multitask. 5. Ignoring diversity and the filter bubble. Most relevant is not best. 6. No cold start plan. New users and items are a huge fraction of traffic. 7. Forgetting train serve skew and the feature store. It's a silent model killer. 8. Judging the system on offline metrics only. The truth is an online A/B test. 9. Ignoring the feedback loop, training on your own biased choices. And 10. Treating it as pure ML with no systems, no Kafka, no feature store, no latency budget. A recommender is a systems problem as much as a modeling one. So, a recommendation system is a funnel, not a model. You can't score 100 million items in 200 milliseconds, so you stage it. Retrieval narrows millions to hundreds cheaply, using two-tower embeddings and approximate nearest neighbor search, blended across several sources for recall. Ranking takes those hundreds and orders them precisely with a heavy, multitask model fed by a feature store. And re-ranking enforces diversity, freshness, and business rules while fighting the filter bubble feedback loop. Under it all, two life cycles: offline training and pre-computation, online serving in the latency budget, held together by feature consistency. Handle cold start. Trust online A/B over offline metrics and correct for position bias. Get the funnel, and you can design the feed behind YouTube, TikTok, Spotify, or Amazon, and defend every stage. This is where system design meets machine learning. And it's exactly what the top companies test now. Practice this exact interview with an AI interviewer that pushes back, free at crackit.io. Design the system, then go defend it. See you in the next one.